What if the next trillion-dollar economy exists beyond Earth? By the end, you will understand the interconnected breakthroughs that could turn space from a destination into a self-sustaining economic engine. How do you manage supply chains across millions of kilometers? And what happens when property rights do not exist beyond Earth, as humanity pushes into orbit toward the Moon and eventually to Mars? The old economic rules written for a planet with air, water, and gravity stop making sense. Resource scarcity, growth limits, and the sheer hostility of vacuum and extreme distance demand a completely new system. This is not a science fiction fantasy. It is a technological and economic puzzle that must be solved for long-term survival and prosperity. The first fundamental difference between space and Earth economies lies in something we take for granted every second. Does the challenge of building an economy from nothing inspire or intimidate you? On Earth, gravity is a silent partner in every transaction. It holds our atmosphere in place, keeps water liquid on the surface, and lets us build factories that rely on air pressure and predictable falling speeds. None of that exists in space. Step outside a pressurized habitat and you face instant vacuum, extreme temperature swings, and zero gravity. The economic assumptions we inherit from our planet, that raw materials are cheap, that energy is moderately priced, and that moving goods cost a fraction of their value, collapse entirely. In space, there is no free lunch from nature. Every breath of air, every drop of water, every scrap of thermal insulation must be either hauled up from Earth at enormous expense or extracted and processed locally, which requires its own massive upfront investment. Consider the simple act of shipping a bottle of water from Earth to low orbit. That bottle costs more per kilogram than solid gold today. So if you want to build anything in orbit, a station, a factory, a fuel depot, you face a brutal arithmetic. You can either pay a fortune to lift raw materials from the ground, or you can spend even more to set up mining and refining equipment on a barren rock like the Moon or an asteroid. And here is where the inversion happens. In the terrestrial economy, mass is cheap and energy is often the limiting factor. You can buy a ton of steel for a few $100s, but heating it to melting point costs real money. In space, the opposite is true. The sun floods the region with energy at no cost. A square meter of solar panel in orbit captures many times the power it would on Earth without clouds or night. So energy becomes abundant and nearly free. But mass, every kilogram you want to move, every piece of machinery, every hull panel, every human, comes with a price tag so high it would bankrupt a small nation. This flips conventional economics upside down. The profit motive shifts from minimizing energy consumption to minimizing mass. You design everything to be as light as possible, even if that means using more energy in production. You build with materials found on site: regolith, asteroidal metals, water ice because you cannot afford to ship them. And you reuse everything because waste is not just an environmental concern, it is a financial catastrophe. These are not mere adjustments to existing models. They require rebuilding core economic ideas from the ground up. Supply and demand, comparative advantage, the very concept of cost, all of it must be rethought in a place where the sun gives you power for free, but every atom of carbon or nitrogen you bring from home costs more than its weight in platinum. This fundamental shift sets the stage for an economy that looks nothing like the one we know, and the first step toward building it is deciding what we actually want to produce up there and what we are willing to leave behind. The price of a single kilogram in orbit has dropped dramatically, but it remains absurdly high. During the Space Shuttle era, launching payload cost roughly $60,000 per kilogram in today's money. That is like strapping a luxury car to a rocket and burning it up every time you want to send a modest satellite to space. Even with the arrival of reusable rockets like the Falcon 9, the cost has fallen to around $2,700 per kilogram. That is still more than the price of a high-end smartphone for every single kilogram you lift. And you need millions of kilograms of water, food, construction materials, and machinery to begin building a self-sustaining economy beyond Earth. At those rates, the total bill quickly becomes astronomical. The problem is not just the price tag. It is that the bottleneck remains the same as it was 50 years ago. Every kilogram you bring from Earth must climb out of a deep gravity well at enormous energy expense. Reusable rockets help because they do not throw away an entire vehicle each flight, but the propellant itself costs money, and the rocket still has to haul heavy fuel tanks. The real breakthrough happens when reuse becomes not just landing the booster but refurbishing the whole vehicle quickly and cheaply, like an airliner after a flight. That is where the next generation of vehicles aims to go. The Starship system, for example, targets a launch cost of roughly $100 per kilogram once it achieves full and rapid reuse. That is a 27-fold reduction from current prices, but even that number may not be low enough for a mass-based economy that needs to move tens of thousands of tons annually. Imagine wanting to build a modest orbital fuel depot. You would need to lift hundreds of tons of water and structural components. At current Falcon 9 prices, that single depot would cost billions. At the Starship target, it would drop to tens of millions, which is still a serious investment, but begins to make economic sense if the depot enables even bigger returns. However, the space economy will only truly flourish when launch costs fall below about $50 per kilogram, and ideally into the single digits. That requires pushing beyond chemical rockets and partial reuse. It demands full reusability, orbital refueling to allow the same vehicle to make multiple trips, and eventually new propulsion technologies such as nuclear thermal engines or advanced electric thrusters that move cargo far more efficiently once it is already in space. Each of these advances attacks the cost barrier from a different angle. Full reusability reduces the per-flight hardware waste. Orbital refueling lets a rocket leave Earth with less propellant and top off in orbit, meaning it can carry more payload for the same launch cost. And high efficiency in space propulsion means that once materials are in orbit, they can be shipped to the Moon or asteroids at a fraction of the energy cost that would be needed if the same journey had to be done with chemical engines. Taken together, these technologies can slash the effective cost of moving mass from the surface to deep space by a factor of 100 or more. That is not just an incremental improvement. It is the difference between a niche activity and a genuine economic revolution. And the first of these breakthroughs, full reusability, is already being tested today. And that is where the second breakthrough becomes even more critical. Even with cheap launch costs, hauling every kilogram of water, air, and building material from Earth is a losing strategy for any long-term economy. The real revolution begins when we stop thinking of space as a place we visit and start treating it as a place we use. This is the core idea behind in-situ resource utilization, known as ISRU. It is the practice of living off the land but on a cosmic scale. Instead of shipping everything from home, we extract what we need from the worlds around us. The most immediate and valuable resource in the inner solar system is water. We used to think the Moon was bone dry, but over the past 2 decades, orbiters have confirmed vast deposits of water ice in permanently shadowed craters at the lunar poles. On Mars, water ice lies just beneath the surface across much of the planet. That water is pure gold in space, not because of some rare chemical property, but because it can be split into hydrogen and oxygen, the 2 ingredients for rocket propellant. So imagine a simple operation. A robotic miner lands on the moon, drills into the frozen soil, heats it, and collects the vapor. That vapor is then piped into a processing unit where electricity from solar panels splits the water molecules. The hydrogen and oxygen are liquefied and stored. Now you have fuel and oxidizer made on the moon that can be used to return payloads to lunar orbit or even to launch cargo toward Mars. The cost of that propellant is almost entirely the energy and equipment, not the raw material. And since the sun provides energy for free, the marginal cost of producing a kilogram of propellant on the moon could be a tiny fraction of what it would cost to lift that same kilogram from Earth. But ISRU goes far beyond propellant. The same water can be purified for drinking, for growing plants, for radiation shielding. The oxygen can be used for breathing. And the moon and Mars are covered in regolith, a powdery surface material rich in metals and minerals. With the right processing, you can bake that regolith into bricks, extract iron and aluminum, or even produce silicon for solar panels. Researchers have demonstrated that lunar soil, when heated with concentrated sunlight or microwaves, can be fused into solid construction blocks. You could build habitats, landing pads, roads, and radiation shelters directly from the dirt under your feet. No need to launch a single brick from Earth, and every kilogram you produce locally is a kilogram you do not have to pay to launch. Over time, that saving compounds into enormous economic value. This is the moment when space shifts from being a destination we travel to into a source we draw from. An economy built on ISRU grows organically. It starts with a small seed of imported equipment, but once that seed lands, it begins to extract, refine, and manufacture. Each new product reduces the need for Earth imports, and the initial high cost of the equipment is paid back many times over by the value of the resources it unlocks. The math is simple but profound. Every kilogram of water you mine on the moon saves you thousands of dollars in launch costs. Every ton of regolith you turn into a habitat wall is a ton you did not have to lift through the atmosphere. ISRU breaks the umbilical cord to Earth, and with that break, a true space economy can finally begin to breathe on its own. Energy is the real currency of any space economy, and the numbers involved are staggering. A single habitat module for a crew of 6 requires roughly 50 kilowatts just for life support, lighting, and basic operations. Add manufacturing equipment, such as electric furnaces or 3D printers, and that demand shoots into the megawatt range. A modest lunar mining operation that processes 100 tons of regolith per day would need several megawatts of continuous power. Compare that to the International Space Station, which generates about 120 kilowatts from its solar arrays. That is enough for a laboratory, but not for an industrial base. To build an economy in space, you need power on an entirely different scale. The sun is the most obvious source. In low Earth orbit, a square meter of solar panel receives about 1.4 kilowatts of energy, roughly 40% more than the same panel would get at the equator on a clear day. There is no atmosphere to absorb or scatter light, no clouds, no night. That means a solar farm in orbit can deliver energy at a density and consistency that is impossible on Earth. But there is a catch. In low orbit, a satellite spends about a third of its time in Earth's shadow. That shadow period, even if it lasts only 30 or 40 minutes each orbit, means a battery storage system is required to keep life support and critical manufacturing running. The same problem appears on the moon. The lunar day lasts about 14 Earth days, followed by 14 Earth days of night. A solar farm on the surface would operate for half the month and then sit idle unless you store enormous amounts of energy in batteries or rely on another power source to bridge the gap. This is where nuclear fission enters the picture. A small fission reactor like the one NASA has been developing under the Kilopower project can produce about 10 kilowatts continuously for a decade or more using a compact uranium core. The system weighs roughly 1,500 kilograms, which is heavy to launch, but once deployed, it provides constant power day and night with no dependence on sunlight. Scale that up to a megawatt-class reactor, and you have a power plant that can run an entire lunar base or a fleet of manufacturing robots. The reactor itself would need to be lifted from Earth, but the fuel is so energy-dense that a single launch could provide power for years. Compared to building and maintaining a giant battery bank for a lunar solar farm, a fission reactor becomes economically attractive for any base that needs reliable round-the-clock power. Fusion remains the long-term dream. If we could harness the same reaction that powers the sun, we would have nearly unlimited energy from a fuel source that is abundant in the solar system. Helium-3, for example, is rare on Earth but may exist in large quantities on the Moon's surface, deposited by the solar wind. A fusion reactor running on helium-3 and deuterium would produce energy with almost no radioactive waste. But the technology is still decades away from a practical commercial reactor, even on Earth. In space, the engineering challenges of magnetic confinement or inertial confinement are compounded by vacuum, radiation, and the need for extreme reliability. So while fusion is the holy grail, the immediate path to abundant energy runs through fission and advanced solar. But solar does not have to be limited to the surface. Orbital solar arrays placed in highly elliptical orbits or at the Lagrange points can see sunlight nearly continuously. These arrays could be enormous, spanning kilometers across, and beam the energy down to a lunar base or a manufacturing facility using microwave or laser transmission. A ground station on the Moon, consisting of a mesh of receiving antennas, could convert those microwaves back into electricity with efficiency above 50%. The concept is known as space-based solar power, and it has been studied for decades as a way to provide clean energy to Earth. In space, it makes even more sense because you already live in the environment where the energy is collected. No atmospheric losses, no weather, and the receivers can be placed next to the industrial load. Beamed power also solves the mobility problem. A mining rover that needs to travel kilometers from the base can have a small receiving dish on top and draw energy from a central transmitter, rather than carrying heavy batteries or a dedicated reactor. That flexibility reduces the mass and cost of every vehicle and tool in the space economy. Once you have a high-power beam system in place, you can power construction robots, drilling rigs, and even propulsion for cargo tugs without needing a separate power source at each location. The cost of all this is not trivial. A megawatt-scale orbital solar array with beamed power would require multiple heavy launches for the solar panels, the transmitter, and the support structure. But once built, it delivers energy at a marginal cost approaching zero. The same logic applies to a fission reactor: high upfront cost, incredibly low operating cost. In a space economy where every kilogram of mass must be justified, the most efficient path is to build a few large power plants and distribute the energy rather than scattering small generators everywhere. And with abundant, cheap energy, a whole world of manufacturing possibilities opens up. You can melt metals, sinter ceramics, produce propellant, and fabricate electronics. Without that power, the space economy remains a fragile outpost. With it, the outpost becomes a thriving industrial hub. In that industrial hub, the very absence of gravity becomes a tool. On Earth, every manufacturing process fights against a constant downward pull that causes heavier elements to sink and lighter ones to rise, creating impurities and imperfections in materials. In microgravity, that separation vanishes. Fluids float, crystals grow without touching container walls, and molten metals mix evenly. This opens up a class of products that are nearly impossible to make on Earth, or at best prohibitively expensive. Take fiber optics as an example. The highest quality optical fibers are drawn from a glass preform that must be exceptionally pure. Even microscopic bubbles or density variations scatter light and degrade signal strength. On Earth, gravity causes convection currents in the molten glass, stirring in tiny imperfections. In microgravity, those currents disappear. Researchers have shown that fibers drawn in orbit can have far lower signal loss than any terrestrial version. Such fibers would be invaluable for long-distance communications, data centers, and undersea cables. A single kilometer of space-made fiber could replace many kilometers of Earth-made fiber, and telecommunications companies would pay a premium for that performance. Then there are pharmaceuticals. Several of the most effective drugs today depend on proteins that fold into complex three-dimensional shapes. Understanding that shape is critical for designing new medicines. The best way to determine a protein's structure is to grow a pure crystal of it and then shine X-rays through the crystal. On Earth, gravity distorts the growth process, causing defects and making crystals smaller. In microgravity, protein crystals can grow larger and more perfectly ordered. The result is higher resolution structural data that accelerates drug discovery. Pharmaceutical companies have already flown experiments to the International Space Station to grow crystals of potential cancer and arthritis treatments. The value of a single successful crystal that reveals a new drug target can be in the hundreds of millions of dollars. A small orbital factory dedicated to protein crystallization could serve the entire global pharmaceutical industry, and the shipping cost of the tiny crystal back to Earth would be trivial compared to its market price. Metals and alloys also benefit from the absence of gravity. Some combinations of elements simply do not mix uniformly on Earth because one metal is much denser than the other. Lead and aluminum, for example, separate like oil and water. In microgravity, they can be blended into a homogeneous alloy with unique properties, such as high strength and low weight or excellent radiation shielding. Similarly, foamed metals, where gas bubbles are trapped inside a solid matrix, can be made with far more uniform pore structures in orbit. These materials have applications in lightweight construction, impact absorption, and thermal insulation. There is no factory on Earth that can produce them at scale. Building a factory in space to make these products is not easy. The facility must be pressurized, temperature-controlled, and shielded from radiation. It needs power, raw material handling, and automated manufacturing equipment that can operate remotely with minimal human intervention. Automation is essential because sending a crew to supervise every batch would drive costs through the roof. Robots can load raw materials, start the heating and cooling cycles, monitor crystal growth, and package the finished goods for return to Earth. The initial investment is huge, but the payoff comes from selling a small number of high-value products. The economic trade-off is clear. For bulk commodities like steel or concrete, it will always be cheaper to make them on Earth, even with free solar energy in space. The cost of building and maintaining a vacuum-tight facility among the stars is just too high. But for products where a single gram can be worth thousands of dollars, the math flips. A space factory that produces a few kilograms of ultra-pure optical fiber or a handful of perfect protein crystals each year can generate revenue that dwarfs its operating expenses. Those early profits become the seed money for expansion, funding the next factory and the next. And as the factory network grows, the cost per kilogram of production falls, opening the door to increasingly common materials. These premium exports are the bootstrap that a space economy needs. They do not require a mass market or a giant customer base on Earth. A handful of pharmaceutical companies and telecom giants can provide enough demand to justify the first orbital manufacturing plants. Once those plants are profitable, the infrastructure they build becomes a platform for everything else. And that platform, once it exists, changes the calculation for every other industry looking up at the stars. Among the most promising exports for a space economy is energy itself. Space-based solar power, or SBSP, takes the concept of a solar farm and scales it into orbit. Imagine a set of enormous collectors spanning kilometers across, sitting in a geostationary orbit where sunlight is constant and intense. Those collectors convert sunlight into electricity, then beam that electricity down to Earth as a focused microwave stream. On the ground, a network of receiving antennas, often called a rectenna, catches the microwaves and converts them back into electricity that feeds directly into the power grid. The result is a clean, continuous source of baseload power that never stops, no matter the weather or time of day. A single SBSP satellite could deliver a gigawatt or more of power, enough to run a major city. The concept has been around since the 1970s, but the technical and economic hurdles have kept it on the drawing board. The biggest challenge is beam efficiency. A microwave beam spreads as it travels, and even with a focused transmitter, some energy scatters and is lost. Current designs aim for end-to-end efficiency of roughly 50 to 60%, meaning you lose nearly half the energy before it reaches the grid. That is acceptable given that the input energy from the sun is free, but it does demand enormous collectors and precise pointing to minimize losses. The infrastructure cost is also staggering. Each SBSP satellite would require multiple heavy launches to place thousands of tons of hardware into geostationary orbit. The rectenna on the ground would cover many square kilometers and represent a significant investment. But compared to building hundreds of terrestrial solar farms or nuclear plants, the costs become competitive, especially when you factor in the ability to deliver power to remote regions or disaster zones without needing fuel supply line. On Earth, even the best solar farms produce power only during daylight and suffer from cloud cover. Wind farms are intermittent. Nuclear plants provide baseload but require waste management and public acceptance. SBSP offers a clean, always-on alternative that can be located anywhere on the planet, as long as a rectenna can be built. The economic viability improves as launch costs fall. At current Falcon 9 prices, building a single gigawatt SBSP satellite would cost hundreds of billions, making it uneconomical. But with fully reusable vehicles targeting launch costs below $100 per kilogram, that same satellite could cost roughly 10 to 20 billion, which is competitive with a large nuclear power plant. And once the satellite is in place, operating costs are minimal. No fuel, no emissions, and a lifespan of 20 to 30 years. The revenue from selling that much clean energy could run into the billions annually per satellite. For the first time, space would be exporting a commodity that everyone on Earth needs: a cheap, reliable electricity. That revenue stream would then fund further expansion of the space economy. The profits from SBSP could pay for more orbital factories, more mining operations, and more infrastructure. It could break the cycle where everything in space depends on Earth money, because now Earth would be paying space for a resource. Energy is the ultimate commodity, and once it flows from orbit to the ground, the economic relationship between Earth and space is transformed. That transformation opens the door to the next logical resource opportunity. Beyond energy, the solar system is filled with raw materials that are scarce or valuable on Earth, and the richest deposits may not be on a planet or moon at all. They float freely in the form of asteroids. A single metallic asteroid can hold more platinum than has ever been mined on Earth. That is not an exaggeration. Some of the larger near-Earth asteroids, chunks of rock and metal left over from the solar system's formation, contain staggering concentrations of platinum group metals like platinum, palladium, and rhodium. One asteroid just a few hundred meters across could contain tens of thousands of tons of those metals. At current market prices, that single rock could be worth trillions of dollars. And metals are not the only treasure. Many asteroids are rich in nickel and iron, the same materials used to build skyscrapers and bridges. but in space, those materials are valuable because you do not have to launch them. They are already there. Even more critical is water. Many asteroids, especially the carbon-rich C-type asteroids, contain significant amounts of water ice locked within their porous structure. That water can be split into hydrogen and oxygen for rocket fuel, or used directly for drinking and radiation shielding. In the economy of space, water is the most versatile resource of all. The economic incentive to mine an asteroid becomes overwhelming if transportation costs drop low enough. Imagine a robotic spacecraft rendezvousing with a near-Earth asteroid. It lands on the surface, which in microgravity is more like docking with a floating mountain. The spacecraft drills into the regolith, heats the material, and captures the volatiles. It separates the metals from the silicates using magnetic or electrostatic methods. Then it stores the refined products. For metals, the plan is to return them to Earth orbit or directly to the ground. For water, the plan is to sell it on site as propellant for orbital fuel depots. That propellant could then power tugs that move cargo between Earth, the Moon, and Mars. The economics work because a single ton of water from an asteroid costs only the energy and equipment to extract it, not the thousands of dollars per kilogram to lift it from Earth. When you have a steady supply of cheap propellant in orbit, every other space activity becomes cheaper. Launch costs from Earth no longer dominate the budget. Missions can be refueled in space, extending their lifetimes and reducing the number of expensive launch vehicles needed. The entire industry becomes more sustainable. But the challenges are enormous. Prospecting is the first hurdle. We have catalogued thousands of near-Earth asteroids, but we know little about their exact composition from a distance. Telescopes can hint at their mineral content, but you need a spacecraft to fly by or land to confirm what is really there. Several missions have done that. The Japanese Hayabusa 2 mission returned samples from the asteroid Ryugu, and NASA OSIRIS-REx brought back material from Bennu. Those missions proved we can reach an asteroid, touch it, and bring samples home. But they were scientific expeditions, not commercial ones. They cost hundreds of millions of dollars and took years. A mining operation must do the same thing at a fraction of the cost and on a faster timeline. That requires heavy automation and robotic systems that can operate without real-time human control, because the communication delay to even a near-Earth asteroid can be several seconds. The extraction process in microgravity is also tricky. On Earth, you dig with shovels and bulldozers. In microgravity, a shovel would just push you backward. You need to anchor yourself to the asteroid first, then use drills that can grip the surface without causing the whole rock to spin away. Techniques like using a harpoon or a clamp are being studied. Once you break the regolith loose, you have to contain it. Dust and fragments will float everywhere, potentially clogging filters and damaging equipment. Processing in zero gravity requires centrifuges or magnetic separators that work without gravity to stratify materials. All of this adds complexity and cost. The location of the asteroid matters greatly. Near-Earth asteroids, those that come within a few million kilometers of our planet, are the easiest targets. They require less energy to reach and less fuel to return cargo. Their orbits are often similar to Earth's, making round trips feasible in months or a few years. The main belt, located between Mars and Jupiter, contains far more asteroids and far richer resources, but reaching them takes years and far more delta V, the measure of change in velocity required. For the early mining economy, near-Earth asteroids are the obvious starting point. Their abundance of water and metals, combined with relatively low travel costs, makes them the low-hanging fruit of the solar system. The role of robotic missions is central. No human crew will be sent to an asteroid for a long time because the cost of keeping them alive in deep space is prohibitive. Instead, fully autonomous robots will do the work. They will land, assess the composition, drill, process, and package the output. Then a robotic tug will carry the cargo back to Earth orbit or to a lunar fuel station. All of this must work perfectly without human intervention because there is no one there to fix a broken drill. That level of autonomy is being developed today for terrestrial mining and for planetary rovers. The gap between current technology and what asteroid mining requires is narrowing. If water from an asteroid can be sold as propellant in orbit, the market is immediate. Every satellite that needs to change orbit, every spacecraft headed to the Moon or Mars, every space station that needs to boost its altitude requires propellant. Today that propellant comes from Earth at high cost. Tomorrow it could come from a nearby asteroid at a fraction of the price. The fuel depot becomes the hub of a new orbital economy. Asteroid mining remains speculative. No company has yet successfully extracted a single gram of material from an asteroid for profit. The legal framework for owning resources in space is still being debated. The initial investment would be enormous, likely tens of billions of dollars, and the returns would take years to realize. But if solved, asteroid mining would transform the human presence in space from a dependent outpost into a self-sustaining civilization. It would provide the raw materials for orbital factories, the fuel for deep space travel, and the metals for everything from spacecraft hulls to solar panels. The economic engine would no longer rely solely on Earth. It would draw directly from the solar system's vast reservoir of resources, and that is the kind of transformation that turns a speculative idea into an inevitable future. Every economy runs on logistics. Without a reliable transport network, the richest asteroid in the solar system is just an unreachable pile of rocks. The vision of a self-sustaining space economy hinges on moving people, goods, propellant, and machinery between Earth, the Moon, Mars, and orbital stations. That requires a transportation backbone as sophisticated and efficient as the global shipping system we rely on today, but adapted to the vacuum and distances of space. The concept is called a Cis-Lunar supply chain, and it is the invisible skeleton that will support every other activity beyond Earth. The core of this supply chain is a network of orbital depots. Think of them as gas stations and warehouses floating in space. A depot sits in a stable orbit, usually in low Earth orbit or at the Lagrange points, those gravitational balance points between Earth and Moon. The depot stores propellant, water, food, spare parts, and finished goods. It is refueled by tankers launched from Earth or by shipments from lunar and asteroid mining operations. From the depot, smaller transfer vehicles known as space tugs take over. These tugs are designed to move cargo between orbits without wasting fuel. They are reusable, slow but efficient, and powered by electric thrusters that use far less propellant than chemical rockets. A tug can gently push a container of lunar water from the Moon's orbit to the depot, or carry a load of Martian supplies from Earth orbit toward the Red Planet. The vehicles that actually land on planetary surfaces must be reusable landers. Unlike Apollo, where each lander was discarded, a reusable lander can shuttle between an orbiting depot and the surface dozens of times. On the Moon, a lander might carry a full load of refined regolith bricks up to orbit, then descend again with a fresh batch of supplies from Earth. On Mars, the atmosphere adds complexity, but the same principle applies. A lander that can refuel on the surface using locally produced methane and oxygen becomes a workhorse. The Starship design aims for exactly this capability, using in-situ refueling to make multiple round trips. Standardization is the secret weapon of any efficient logistics network. On Earth, the shipping container transformed global trade because every truck, train, and ship used the same box size and attachment points. Space needs the same revolution. Every orbital depot, every tug, every lander, every storage module must use a common interface for docking, power transfer, data, and cargo handling. Imagine a standard pallet size for space cargo, with built-in handles for robotic arms and standard electrical connectors. A mining operation on the Moon could load its products into a standard container, and that container could be transferred from a lunar lander to a space tug, then to an orbital depot, and finally to a return craft heading to Earth, all without anyone having to repack a single item. This is not just convenience, it is economic necessity. Without standardization, every transfer would require custom equipment, driving costs sky high and killing the margins that make space commerce viable. The most critical cargo in the early stages is propellant. Water is the universal currency of space logistics because it splits into hydrogen and oxygen. A depot that holds tens of tons of water can support dozens of missions. A tug that picks up a container of water from a lunar source and delivers it to a waiting lander at the Earth-Moon Lagrange point is performing the most valuable transaction in the Cis-Lunar economy. The propellant itself becomes a commodity that is produced, stored, and traded just like crude oil on Earth. And the cost of that propellant, once the infrastructure is in place, will be a tiny fraction of what it costs to launch from Earth. But none of this works without reliable human infrastructure alongside it. The transport network cannot scale without people to maintain it, operate the depots, and oversee the increasingly complex movements. Whether those people live in a space station, a lunar habitat, or a Martian base, they need support systems that are just as standardized and modular as the cargo containers. Life support, food production, waste recycling, and medical facilities must plug into the same logistics framework. The depots become not just fuel stops, but settlements where crews can live, work, and repair equipment. The space tugs are not just robots, they carry technicians who can service a broken satellite or assemble a new section of a habitat. The economics of scale kick in when the transport network reaches a tipping point. Once you have a few depots, a fleet of reusable tugs, standardized containers, and reliable landers, the cost of moving mass between Earth and the Moon drops by orders of magnitude. That cost reduction feeds back into every other industry. More mining becomes profitable, more factories can be built, more people can live in space. The transportation backbone is not just a support system. It is the circulatory system that delivers resources to every part of the body of the space economy. And as that system strengthens, the next logical question emerges. How do we design the homes and workplaces that these supply lines are meant to feed? A permanent home beyond Earth requires solving problems we have never faced before. The International Space Station proved that humans can live in orbit for over a year, but it is a laboratory, not a settlement. It relies entirely on regular resupply missions from Earth, and its crew stays for only 6 months at a time. A true space economy demands habitats that function continuously for decades or centuries, supporting humans who may never return to Earth. That changes every design decision. The first and most formidable threat is radiation. In space, beyond the protective bubble of Earth's magnetic field, astronauts are bombarded by galactic cosmic rays and solar particle events. High-energy particles can damage DNA and increase cancer risk. On a lunar base or a Martian colony, the ground itself becomes a shield, covering a habitat with a few meters of regolith. The loose rock and dust on the surface blocks nearly all of that radiation. The same material can be used to build walls, roofs, and underground chambers. On the Moon, where there is no atmosphere, a habitat buried under a meter of dirt offers protection roughly equivalent to Earth's surface. On Mars, combining the thin atmosphere with a meter of regolith brings radiation levels close to those in a typical terrestrial city. On an orbital station, no such ground exists. Orbital habitats must rely on water storage, polyethylene panels, or active magnetic shields, all of which add mass and cost. This makes surface habitats more attractive for long-term stays, even though they require more infrastructure to land and construct. The second requirement is closed-loop life support. On the space station, most water is recycled, but a significant amount of food and oxygen is still shipped from Earth. For a permanent colony, every molecule must be reused indefinitely. Air must be scrubbed of carbon dioxide and replenished with oxygen. Water from showers, sinks, and even urine must be purified back to drinking quality. Solid waste must be processed into fertilizer for growing plants. Plants themselves play a double role. They produce oxygen and food while recycling carbon dioxide and waste. A fully closed loop is extremely difficult to achieve. Even the most advanced terrestrial greenhouses lose some materials to leakage. Researchers at the University of Arizona have operated compact bioregenerative life support systems that recycle nearly 99% of water and a significant fraction of air, but they require careful monitoring and frequent maintenance. Scaling these systems to support dozens or hundreds of people is one of the great engineering challenges for space settlements. The third challenge is the absence of gravity for long periods. The human body evolved in one gravity. In microgravity, bones lose density, muscles atrophy, fluids shift to the head, and vision degrades. A 6-month stay on the space station requires months of rehab upon return. For a permanent colony, the only proven countermeasure is to create artificial gravity. The classic solution is a rotating habitat. By spinning a torus or cylinder, centrifugal force pushes the occupants toward the outer wall, simulating gravity. A radius of at least 50 meters at a rotation of 2 to 4 revolutions per minute provides a comfortable one-gravity equivalent for most people. Designs for rotating orbital habitats date back to Wernher von Braun and the 1950s, but building such a structure in space remains expensive. On the Moon or Mars, the reduced gravity about 1/6 and 1/3 of Earth's respectively poses less of a threat, but still requires exercise regimens to maintain bone density. Colonists might need to spend several hours each day on exercise machines like the ones used on the space station, or supplement with medication. The psychological effects of living in low gravity for years are still poorly understood, but early studies suggest that with proper equipment and routine, most people adapt. The fourth major factor is psychological. Confinement, isolation, monotony, and the constant threat of equipment failure create mental strain. Crews on the space station receive regular contact with family, private quarters, and scheduled leisure time, but they also face cramped quarters and limited privacy. A permanent settlement will need larger living spaces, windows or virtual windows to the outside, common areas for social interaction, and perhaps even simulated outdoor environments. The design of a habitat must consider not just survival but quality of life. Psychologists have studied crews in Antarctic stations, submarines, and Mars simulation missions to understand what factors keep teams cohesive and productive. They have found that personal space, natural light, greenery, and the ability to pursue hobbies all reduce stress. A colony that fails to address these needs may see high turnover, declining morale, and ultimately abandonment. Building these habitats from materials found on site dramatically reduces the cost. On Earth, shipping 1 kilogram of construction material to the Moon costs thousands of dollars. But that same kilogram, if extracted from lunar regolith, costs only the energy and equipment to process it. 3D printing is the most promising method. Robotic printers can use regolith mixed with a binder or melted by concentrated sunlight or microwaves to create solid blocks, walls, and domes. NASA's 3D printed habitat challenge demonstrated that teams can build full-scale structures using simulated lunar and Martian materials. In practice, a rover would travel across the surface, scoop up soil, process it into a printable paste or sinter it into solid layers, and slowly construct a habitat layer by layer. The result is a sturdy structure that provides radiation shielding and thermal insulation, built almost entirely from local resources. The only parts that need to be brought from Earth are the printers themselves, the electronics, the seals, and the internal fittings. That mass is small compared to the total volume of the structure. Comparing the economics of different habitat locations reveals trade-offs. Orbital habitats are the easiest to reach from Earth and offer microgravity for manufacturing, but they lack local resources. Everything from air to shielding must be lifted, making them vastly more expensive per cubic meter of living space. Lunar bases have abundant regolith for construction and water ice at the poles, and the Moon is only a few days away from Earth. However, the 2-week night requires large energy storage or nuclear power, and the extreme temperature swings place stress on equipment. Martian colonies have a thin atmosphere that provides some protection and allows for easier entry and landing, but the travel time is 6 to 9 months, making resupply slow and costly. On the other hand, Mars has abundant water ice across much of its surface and a day length close to Earth's, which simplifies solar power and circadian rhythms. Over the long term, Mars may be the most economically self-sufficient destination, even though the upfront investment is enormous. Once permanent habitats exist, human presence itself becomes an economic driver. People need food, water, medical care, entertainment, education, and governance. They will want goods and services that go beyond survival. Repair shops, cafes, gyms, and even small retail stores could emerge in a colony. Parents will want schools for their children. People will need legal systems, property rights, and dispute resolution. A colony of a few hundred or a few thousand will generate demand for everything from hairdressers to software developers. That demand creates jobs and markets that are entirely local, not dependent on Earth. The colony becomes not just a place to work, but a place to live, and where life exists, an economy follows. The design of the habitat is not an end in itself. It is the foundation for a new society that will invent its own rules, its own culture, and its own forms of exchange. And that society, once rooted beyond Earth, will need something that no machine can provide: a system of governance that balances individual freedom with collective survival. Third, there is a question that no rocket can solve: who owns the resources beyond Earth? The entire legal framework for space rests on a treaty signed in 1967, the Outer Space Treaty. It states that no nation can claim sovereignty over the Moon or any other celestial body. That seems fair and peaceful, but it also means that no one can own the land itself. And if you cannot own the land, how can you own the minerals you dig out of it? How can a company invest billions into a lunar mine if the legal title to that ore is uncertain? The treaty was written during the Cold War to prevent a territorial scramble in space, but it was not written with commercial mining in mind. It says that outer space is the province of all mankind, which sounds noble but creates a legal vacuum where property rights simply do not exist. The Moon Agreement of 1984 tried to fill that gap by declaring the Moon and its resources the common heritage of mankind. But that phrase implies international ownership and shared profits, a deal that no private company would accept. As a result, the Moon Agreement has been ratified by only a handful of nations, none of the major spacefaring powers. It is essentially a dead letter. That leaves the original treaty as the only widely accepted rule, and it offers no guidance on who has the right to extract and sell water, metals, or any other resource. The Artemis Accords, signed in 2020 by the United States and several partner nations, take a different approach. They affirm that extracting resources is allowed, as long as it is done in a way that respects the Outer Space Treaty. They also establish safety zones around operations to prevent interference. But the Accords are not a binding treaty. They are bilateral agreements between nations, and they have been criticized by countries like Russia and China, who see them as an attempt to claim special privileges. Legal certainty is the bedrock of any economy. Without it, investors face a risk that no insurance policy can cover. If you spend $10 billion building a fuel depot on the moon, and then another nation or a competitor argues that your claim to that site is invalid, your entire investment could vanish in a legal challenge that may take decades to resolve. That uncertainty alone is enough to keep most venture capital on Earth. The same problem applies to orbital slots. Geostationary orbit is a finite resource, a ring 22,000 miles above the equator where satellites can stay fixed over one spot. There are only a limited number of slots, and they are currently allocated by the International Telecommunication Union on a first-come, first-served basis for sovereign nations. Private companies must lease those slots from their home country. As the number of satellites grows and as mega-constellations fill low Earth orbit, the fight for space becomes physical. Collisions threaten satellites worth hundreds of millions of dollars, and there are no clear rules for liability or salvage. Whose job is it to remove a dead satellite? Who pays if a derelict spacecraft smashes into an active one? Beyond property, there is the question of jurisdiction. If a crime is committed in a space habitat, whose laws apply? If a contract is signed between a company on Earth and a factory on the moon, which court has authority to enforce it? Today, every astronaut on the International Space Station is subject to the laws of their own nation, but that is an ad hoc arrangement that works only for a small crew. A colony of hundreds or thousands of people living permanently off Earth will need its own legal system. It will need laws for marriage, inheritance, contracts, and criminal justice that are adapted to the harsh realities of a closed environment where a fire or a breach can threaten everyone. Private companies will not build hotels, factories, or research labs in a legal void. They need to know that their patents will be recognized, their property will not be stolen, and their employees will be protected. That means treaties must be updated, national laws must be extended, and new international agreements must be created. The process is messy and slow, but it is as essential as any rocket engine. Without it, the space economy remains a dream that can never attract the capital needed to become real. On the moon, a financial transaction takes nearly 3 seconds to complete. That is the time it takes for a signal to travel from the lunar surface to Earth and back. An entire sequence of checks, verifications, and confirmations that we take for granted on our planet would stretch into an awkward pause every time a buyer and seller are not standing in the same control room. Now multiply that distance by the trip to Mars, where a message takes between 4 and 24 minutes each way, depending on orbital alignment. A simple question like "Did the payment clear?" could hang in the void for almost an hour. Instant settlement, the backbone of modern banking and stock exchanges, becomes impossible beyond Earth orbit. The foundation of a space economy must therefore be a financial system that does not require real-time confirmation. This shifts the role of money itself. Instead of relying on a central bank that settles every transaction within seconds, the space economy needs a currency that can be exchanged peer-to-peer, with trust built into the code rather than into a distant institution. Digital currencies, especially those built on blockchain technology, offer a natural fit. A blockchain is essentially a shared ledger that records every transaction in a chain of blocks that are cryptographically linked. Once a block is added, it is extremely difficult to alter. That means two parties on opposite sides of the solar system can agree on a transaction, sign it with their private keys, and broadcast it to the network. The network, which consists of computers scattered across Earth and eventually across orbital stations and surface colonies, will verify the transaction and add it to the ledger. No central authority needs to approve it. No long round trip to a clearinghouse is required. The trust comes from the mathematics of the blockchain itself. In practice, a lunar miner can sell a container of water to an orbital fuel depot by sending a digital token representing that water, and the transaction is validated by nodes on Earth and in orbit. The water may be physically transferred hours or days later, but the ownership has already changed hands. This is where tokenization becomes powerful. Any asset, from a ton of regolith bricks to a claim on an asteroid, can be represented as a digital token on the blockchain. The token acts as a certificate of ownership that can be split, traded, or used as collateral. An asteroid mining company, for example, could issue tokens representing a share of the platinum they expect to extract from a specific asteroid. Investors on Earth could buy those tokens, effectively buying a stake in the future output. The asteroid itself may be millions of kilometers away and may not be touched by a human for years, but the financial value can circulate immediately. Smart contracts take this a step further. A smart contract is a self-executing program on the blockchain that automatically carries out the terms of an agreement. Imagine a contract that says if a robotic probe confirms that a water ice deposit contains at least 50,000 kilograms of extractable water, then a payment of 1,000 tokens will be released to the mining operation. The probe sends its data, the smart contract checks the result, and the transfer happens without anyone needing to approve it. No trust in a human intermediary is needed. The code is the agreement. This kind of automation is essential across vast distances because direct oversight becomes impractical. A habitat on Mars cannot wait for an Earth bank to verify every micropayment for food, oxygen, or power. The system must run itself. Commodity-backed currencies also make sense. Instead of a purely digital token whose value is based on speculation, a space dollar could be redeemable for a fixed amount of water, or a kilowatt-hour of solar electricity, or a kilogram of aluminum. That gives the currency intrinsic value tied to the basic resources of the space economy. If you hold a water token, you know you can exchange it for actual water at any depot. That stability encourages trade because everyone knows what the token is really worth. The concept is not new. Satellite operators today already use a form of barter and time exchange. For example, a company that owns a satellite may trade a portion of its bandwidth or imaging time for another company's launch services. These trades are often arranged through complex contracts and third-party brokers. A blockchain-based token system could streamline that process, turning satellite capacity into a tradable digital asset that can be split into seconds of usage and exchanged on a global market. The same principle applies to any space resource: data relay time, power beaming slots, propellant storage space, or even crew quarters on a station. The financial layer must also handle the problem of delay in dispute resolution. If two parties disagree over whether a delivery was made on time, a smart contract can include an escrow mechanism. The payment is locked until a trusted third party or even an automated sensor reading confirms the condition. On Earth, this is called a smart escrow. In space, it becomes a necessity because you cannot call a lawyer in another time zone. You must design the rules into the transaction itself. Building this entire financial infrastructure is not an afterthought. It is as critical as the rockets, the habitats, and the mines. Without a reliable, trustless, and delay-tolerant system for exchanging value, the space economy would stall in the same way that the medieval economy stalled without standardized coinage. The physical machines can move atoms, but the financial machines must move value across the same vast distances. And those machines, running on code and cryptography, may be the first truly automated economy in human history, one where the ledger itself is as permanent as the craters on the moon. The first check for any space economy is written on Earth. Before a single kilogram of regolith is mined, before a single fuel depot is stocked, someone must risk capital on a future that is far from certain. That capital comes in distinct streams, each with its own appetite for risk and its own timeline for returns. Government agencies like NASA and the European Space Agency anchor the early years. They fund the fundamental research, the proof-of-concept missions, the technology demonstrations that private companies cannot afford to do alone. NASA Artemis program, for example, is spending tens of billions to return humans to the moon and build the Gateway station. That spending creates a base of infrastructure, launch contracts, and demand for services that private firms can build upon. Without that government anchor, the risk is simply too high for anyone else to step in. But government money has limits. It is slow, political, and tied to election cycles. It cannot scale fast enough to build a full economy. That gap is filled by private capital, a world of venture funds, special purpose acquisition companies, and high net worth individuals. Venture capital thrives on asymmetric returns. A portfolio of 10 startups, 9 of which fail, can still produce enormous profits if the 10th becomes a SpaceX. The space sector is naturally suited to this model because the barriers to entry are high, but so are the potential rewards. A company that perfects asteroid prospecting or orbital propellant storage could unlock markets worth trillions. That prospect has drawn billions of dollars in private investment over the past decade. Special purpose acquisition companies, or SPAC, offered a shortcut to public markets for space ventures eager to raise capital quickly. Several companies, including those working on satellite constellations and launch vehicles, went public through SPAC in the early 2020s. Some thrived, others struggled, but the mechanism itself demonstrated that Wall Street is willing to bet on the extreme upside, even if it carries extreme risk. Public-private partnerships combine the best of both worlds. A government agency might provide the lander or the habitat design, while a private company operates the logistics and sells services to other customers. NASA Commercial Orbital Transportation Services Program, which funded SpaceX and Orbital Sciences to deliver cargo to the International Space Station, is the classic example. The government paid for development milestones, but the companies kept the intellectual property and could sell the same services to other clients. That model has now expanded to crew transportation, lunar landers, and soon to commercial space stations. It de-risks private investment by guaranteeing an initial customer while letting the private sector innovate and capture new markets. Then there is a unique group, the billionaire philanthropist entrepreneurs. Elon Musk and Jeff Bezos have poured personal fortunes into SpaceX and Blue Origin not just for profit, but to push humanity toward a multiplanetary future. Their time horizons are measured in decades, not quarters. They can tolerate failures that would sink a traditional company because they view space as a grand challenge, almost a cultural mission. Their willingness to fund early-stage infrastructure from their own pockets is a form of philanthropy that happens to generate technological progress. That kind of long-term, patient capital is rare and extraordinarily valuable. It allows projects like the Starship or the New Glenn rocket to move forward without waiting for quarterly earnings reports. All of this investment must eventually flow to people. The labor side of the space economy is just as critical as the capital side. Who works in space and how do they get paid? Early on, most workers will be astronauts, engineers, and technicians on short rotations. But as habitats grow and industries expand, the workforce will diversify. There will be miners, welders, botanists, cooks, teachers, and doctors. Their wages will not be sent back to Earth in the same way. A lunar miner might be paid in digital tokens redeemable for oxygen credits or in shares of the water they extract. A habitat chef might earn a salary denominated in kilowatt hours or in accommodation credits. The concept of a paycheck changes when the employer and employee are separated by millions of kilometers and when the local currency is tied to survival essentials. That transformation of labor and compensation is the next piece of the puzzle, and it will shape the social fabric of every settlement beyond Earth. A welder on the moon earns her salary in tokens redeemable for oxygen credits, and her neighbor is a botanist growing potatoes under artificial sunlight. The workforce of a space economy is as diverse as any city on Earth, but the conditions under which people work are radically different. The first generation of space workers will come from the traditional astronaut corps, engineers trained for years in simulators, centrifuges, and isolation chambers. They will operate the early habitats, maintain life support, and troubleshoot emergencies. But as the economy scales, the need for specialized skills explodes. Miners will learn to operate robotic drills in vacuum, using haptic feedback suits that let them feel the resistance of lunar regolith from a control room on the surface. Farmers will cultivate algae and vegetables in hydroponic racks, carefully balancing nutrients and light cycles to maximize yield per cubic meter. Hospitality workers will staff orbital hotels, training for months to manage the unique challenges of serving meals in microgravity and helping guests adjust to the disorientation of weightlessness. The skill sets required go far beyond the typical engineering degree. A lunar miner must understand geology, robotics, and materials processing. A space farmer needs expertise in plant biology, closed-loop systems, and water recycling. A medical officer on a Martian base must be proficient in emergency surgery, dental care, and mental health counseling because the nearest specialist is months away. Training pipelines will shift from the highly selective astronaut programs of today to more accessible vocational pathways. Community colleges on Earth may soon offer certificates in zero-gravity manufacturing or extraterrestrial agriculture. Virtual reality simulators will let trainees practice repairs on a space station without ever leaving the ground. The most critical skill, however, may be adaptability. In an environment where a single mistake can depressurize a habitat, workers must learn to remain calm under pressure, follow procedures precisely, and think creatively when those procedures fail. Robotics and teleoperation will increasingly reduce the need for humans to be physically present in dangerous locations. A miner on Earth can pilot a drilling rig on the moon from a control center, wearing a haptic glove that transmits the texture of the rock. This removes the need for a human to endure the radiation and dust of the lunar surface, while still leveraging human judgment for complex decisions. Teleoperation works well for tasks with short communication delays, such as operations on the moon where the signal lag is only a couple of seconds. On Mars, where the delay stretches to minutes, autonomous systems become far more important. The robot must decide by itself, and the human only intervenes at a strategic level. That shift means the workforce of the future will include more software engineers and AI trainers, people who can program and supervise autonomous machines rather than operate them directly. Compensation in a space economy will look nothing like a traditional paycheck. Hazard pay is an obvious starting point. Working in a place where the ambient pressure is zero and the temperature swings by hundreds of degrees demands a premium that reflects the risk. But beyond base salary, workers may receive equity stakes in the operation. A miner who helps extract the first 100 tons of water from an asteroid could own a fraction of that resource, paid out when it is sold to a fuel depot. This aligns the workers' incentives with the long-term success of the venture. Another model is a universal basic space income, a guaranteed minimum of credits that covers oxygen, water, and food. This safety net ensures that even if a project fails, no one is left without the essentials of survival. Human factors are the invisible cost of any space workforce. Health risks include bone density loss, muscle atrophy, and increased cancer risk from radiation. Astronauts on the International Space Station exercise 2 hours a day to mitigate these effects, but that routine becomes harder to maintain in a busy mining operation. Isolation takes a deeper toll. The distance from family and friends, the limited communication windows, and the monotony of a confined habitat can lead to depression and anxiety. In the small communities of early colonies, everyone knows everyone and conflicts can be magnified. Mental health support will be essential, from regular video calls with loved ones to onboard psychologists who live alongside the crew. Some organizations are experimenting with virtual reality environments that allow workers to walk through a forest or sit on a beach, providing a psychological escape from the metal walls. All these pressures mean that automation will absorb many of the most dangerous and repetitive tasks, but it will not eliminate the need for human expertise. Machines break down in unexpected ways, require judgment calls that only a trained eye can make, and cannot replicate the creative spark that solves a novel problem. The goal is to design a system where humans do what humans do best, adapt and improvise, while robots handle the drudgery. The workforce of the space economy is not a collection of interchangeable cogs. It is a community of professionals who have chosen a difficult and meaningful path, and the way we train, support, and compensate them will determine whether that community thrives or merely survives. The first customers of that community may not be miners or engineers. They are people willing to pay a fortune for a few minutes of weightlessness, a glimpse of Earth from above, or a night in an orbital hotel. Space tourism is the earliest revenue generator that does not depend on government contracts or speculative asteroid returns. It is cash flow that can be used to build the very infrastructure that the rest of the space economy needs. Today, the market for suborbital flights is small but real. Companies like Virgin Galactic and Blue Origin have flown dozens of passengers on brief trips that cross the boundary of space, offering about 4 minutes of weightlessness and a view of the curved horizon. The price tag for a seat on these flights has ranged from $250,000 to over $500,000. That is an extraordinary sum for a single person, but the customer base exists among ultra-high net worth individuals who spend similar amounts on luxury travel, art, or yachts. The profit margin on each ticket is huge because the variable cost of launching a reusable rocket is relatively low, especially compared to the fixed development cost. As more vehicles come online, competition is pushing prices downward. A handful of companies now target suborbital tickets in the tens of thousands of dollars by the end of the decade, which will open the market to a broader audience. The next step is orbital tourism. The International Space Station has hosted private visitors for years, paying roughly $50 million for a 10-day stay. That price includes transportation, life support, and a cramped but unforgettable experience. Now, commercial space stations are being designed by companies like Axiom Space, Bigelow Aerospace, and others. These stations will be dedicated to private use, offering more comfort, larger windows, and customizable interiors. Axiom plans to attach its first module to the International Space Station in the mid-2020s, then later detach to form a free-flying station. The price for a stay on these stations will start in the tens of millions, but the goal is to bring it down to single-digit millions within a decade. That still sounds astronomical, but compare it to the cost of a luxury Antarctic expedition or a private jet around the world. For a certain demographic, it becomes a bucket list item, and the market is larger than you might think. A study by UBS estimated that space tourism could become a $3 billion per year industry by 2030 and grow to tens of billions by 2040. The margins come from the scarcity of experience. No one else on Earth can offer what a space hotel provides: a sunrise every 90 minutes, the sight of continents sliding beneath, the feeling of floating in a place where human life is a fragile miracle. People will pay a premium for that, and the same infrastructure that supports them, pressurized modules, life support systems, docking ports, and trained crew, can later be used for manufacturing, research, or transit hubs. Tourism effectively acts as the proving ground for habitat technology. Every hotel module that keeps a guest alive and comfortable is a module that could one day house a factory worker or a scientist. The operational experience gained from running a space hotel, from managing waste to handling medical emergencies, directly informs how to run a lunar base or a Mars transit vehicle. The early money from tourists covers the operating costs and partial capital costs of those modules, accelerating the timeline for everything else. Beyond Earth orbit, lunar tourism is the next horizon. A trip around the moon without landing has already been sold. SpaceX announced a mission called Dear Moon, where a Japanese billionaire and a crew of artists will fly around the moon in a Starship. That ticket price is not public, but it likely runs into the hundreds of millions. A landing on the lunar surface would be even more expensive, requiring specialized landers, suits, and support infrastructure. Still, a handful of clients have the resources and the desire. A single lunar mission could fund months of research or habitat construction. Mars flybys are the ultimate luxury travel. A mission that loops around Mars and returns to Earth, taking about a year and a half, would be the most expensive vacation in history. Only a few individuals could ever afford it, but their payments would be large enough to subsidize the first human mission to the Red Planet for scientific purposes. Tourism creates demand for hospitality infrastructure that would not exist otherwise. Hotels need kitchens, sanitation, entertainment systems, medical bays, and crew. Those same facilities can serve as backup living quarters for a growing population. The tourism dollar is the fuel that powers the first stage of a rocket that will eventually carry the entire economy. As prices fall and capacity grows, the line between tourist and worker will blur. A person who visits a space hotel for a week may later decide to take a longer contract as a technician or a guide. The early exposure creates a trained, familiarized population that reduces the risk of hiring permanent staff. Space tourism is not a distraction from the serious business of building an economy. It is the engine that gets it started. It turns dreams into revenue and revenue into infrastructure. And once that infrastructure exists, it becomes available for every other purpose that follows. While tourism captures the imagination, satellite communications already generate billions in annual revenue. This is the one sector of the space economy that has been profitable for decades, and it keeps growing. Companies like SpaceX and OneWeb are building vast networks of hundreds or even thousands of small satellites that beam internet signals to every corner of the globe. Starlink, the largest of these constellations, now serves over 1 million subscribers, from remote farms in rural America to fishing boats in the middle of the Pacific Ocean. The business model is straightforward. Sell a subscription for a terminal and monthly service, and the customer gets high-speed internet where no cable or fiber can reach. The demand is enormous. Half the world still lacks reliable internet access. Even in wealthy countries, many rural and mountainous areas have spotty coverage. Satellites operating in low Earth orbit can fill those gaps with latency low enough for video calls and online gaming. The same hardware that connects a village in the Amazon also connects a research station in Antarctica. That global reach creates a massive addressable market, and the more satellites you launch, the better the coverage and the lower the per-user cost. Each satellite costs roughly $1 million to build and launch, but once in orbit it can serve thousands of customers for years. The math works. OneWeb and Amazon's Project Kuiper are pursuing the same strategy, driving competition that pushes prices down and speeds up deployment. Alongside communications, Earth observation is the other cash cow. Hundreds of satellites constantly photograph and scan the planet, gathering data that farmers, insurers, governments, and energy companies pay for. A wheat farmer in Kansas can receive weekly images that show exactly which parts of the field are dry or diseased. allowing precise irrigation and pesticide application. That saves money, increases yield, and reduces environmental impact. Climate scientists use the same data to track deforestation, monitor ice sheet melt, and predict weather patterns. Even urban planners rely on satellite imagery to map traffic congestion or assess damage after a natural disaster. The military and intelligence agencies are enormous customers, purchasing high-resolution imagery of sensitive areas, but the commercial market is also booming. A single satellite imaging company like Planet Labs operates hundreds of small satellites called doves that image the entire land surface of Earth every day. Their customers pay annual subscriptions for access to that stream of images. The revenue is steady and predictable. These services do not require revolutionary new technologies. They use proven hardware and software, and they generate consistent cash flow year after year. That cash flow is the fuel that powers everything else. The companies that dominate satellite communications and Earth observation, such as SpaceX and Planet Labs, reinvest their profits into developing cheaper launch vehicles, more efficient manufacturing techniques, and advanced in-space propulsion. Without the billions of dollars flowing from internet subscriptions and image sales, the research and development needed for lunar mining or orbital factories would have to rely entirely on government grants and speculative venture capital. Instead, the profitable satellite sector provides a self-sustaining engine of innovation. It pays for the engineers who design reusable rockets, the factories that churn out thousands of satellite components, and the launch pads that send them into orbit. Every time a Starlink satellite is built and launched, the lessons learned about mass production and low-cost manufacturing apply directly to building habitat modules or asteroid probes. The satellite economy is not a separate industry. It is the foundation on which the rest of the space economy stands. The next logical service to emerge from this foundation is on-orbit servicing. Satellites today are disposable. They launch, operate for a decade or so, run out of fuel or suffer a failure, and then become space debris. But if you can send a robotic spacecraft to refuel a satellite, repair its solar panel, or extend its mission, you unlock enormous value. Geostationary communications satellites, which cost hundreds of millions each, can earn revenue for an extra 5 or 10 years if they are given a fresh tank of propellant. The same logic applies to Earth observation satellites. Instead of launching a costly replacement, you send a servicer to fix the aging hardware. Several companies are now testing these capabilities, using robotic arms and specialized docking mechanisms. The technology is complex, but the economic incentive is clear. A servicer that can refuel a single high-value satellite earns its own development cost in one mission. As the satellite constellation grows, so does the market for servicing, refueling, and eventually recycling those satellites instead of abandoning them. That service turns waste into value, and it prepares the technical skills needed for even more ambitious tasks, such as assembling large structures in orbit or repairing a human habitat. The profitable satellite sector has already paid for the rockets and the manufacturing lines. Now it will pay for the robots that keep the machines running, and in doing so, it will write the next chapter of the space economy. A single satellite in geostationary orbit can cost $400 million to build and launch. It is a marvel of engineering, packed with transponders and solar panels, designed to beam television, internet, and phone signals across entire continents. Yet after a decade or so, it begins to run out of station-keeping propellant. The electronics may still work perfectly. The solar arrays may still generate power. But with no fuel left to maintain its precise orbital slot, the satellite is drifted into a graveyard orbit and retired. All that value, hundreds of millions of dollars, is essentially thrown away because nobody bothered to top off the tank. That waste is the driving force behind a new industry called on-orbit servicing. The idea is simple. send a robotic spacecraft to rendezvous with an aging satellite, dock with it, and perform maintenance that keeps it operational. NASA demonstrated the first step with a mission called Restore-L, later renamed on Orbit Servicing, Assembly, and Manufacturing 1, or AWESOM-1. That spacecraft was designed to approach a government satellite in low Earth orbit, use a robotic arm to cut through the insulating blanket, and then refuel it through a specialized port. The mission faced delays and technical hurdles, but the principle was proven. A robot can delicately work on a satellite that was never built to be touched in space. Private companies quickly saw the commercial opportunity. Instead of building and launching a replacement satellite that costs $500 million, a customer could pay a fraction of that for a refueling mission. A single tanker carrying a few hundred kilograms of hydrazine propellant could extend the life of a geostationary communications satellite by 5 to 10 years. That extra revenue, at tens of millions of dollars per year, makes the service price look like a bargain. Several companies, including Northrop Grumman with its mission extension vehicle, have already performed successful dockings with commercial satellites in geostationary orbit. The mission extension vehicle latches onto the satellite using a grappling mechanism and then uses its own thrusters to keep the satellite in the correct orbital slot. The satellite never even needs to be designed for refueling. The servicer simply acts as an external propulsion module. Beyond refueling, repair becomes the next frontier. A satellite that loses a solar panel due to a micrometeoroid impact or suffers a stuck antenna can be visited by a servicer that carries spare parts. A robotic arm with precision tools can cut away damaged wiring, install a new component, or adjust a mechanism that has jammed. This is far more complex than simply providing propulsion, but the payoff is even larger because it can save a satellite that would otherwise be a total loss. The economic incentive compounds. A single high-value satellite generates millions in revenue each week it stays online. A repair that costs $50 million and restores a year of operation is a huge win for the owner. As these capabilities mature, a natural shift occurs. If you can dock with a satellite and manipulate its parts, you can also assemble new structures from components launched separately. Instead of launching a massive space telescope folded up inside a rocket fairing, you can send up the mirrors, the truss, and the instruments as separate packages, then have a robotic servicer connect them in orbit. The James Webb Space Telescope required a decade of development and $1 billion unfolding sequence because it had to fit inside a single launch vehicle. An assembled telescope could be far larger, with a mirror 20 or 30 meters across without the same engineering nightmare. The same logic applies to space stations. Future habitats can be built in orbit from modules that are too bulky to launch in one piece, connected by robotic arms and secured with bolts driven by automated tools. The very same robots that once refueled a communication satellite will eventually bolt together the skeleton of a space station, and that station, in turn, can host more manufacturing equipment, creating a cycle that builds upon itself. On-orbit servicing is not just a repair business. It is the first step toward the orbital construction yards that will build the next generation of everything that flies in space. The most valuable products made in orbit are not metals or fuel, but ultra-pure glass and perfect crystals. Consider a material called Z-blan, a type of fluoride glass that can carry light signals with far less loss than the silica fibers used in today's internet cables. On Earth, gravity creates tiny density variations and microscopic bubbles as the glass cools, scattering the light and limiting the distance a signal can travel without amplification. In microgravity, those defects vanish. A Z-blan fiber drawn in orbit can transmit a signal over 1,000 kilometers without needing a booster, compared to about 100 kilometers for the best terrestrial fiber. Telecommunications companies are already hungry for that kind of performance. because fewer amplifiers means lower cost and higher reliability in undersea cables and long-haul networks. The global fiber optic market is worth tens of billions of dollars each year, and even a modest share of that market, say a few tons of Z-band preform per year, could generate hundreds of millions in revenue. The price per kilogram of this space-made glass would be thousands of dollars, far higher than ordinary fiber, but the performance justifies the premium. The same principle applies to protein crystals. Many of the most advanced drugs, from cancer treatments to arthritis therapies, are built around proteins whose three-dimensional shape determines how they interact with the body. To design a better drug, scientists need an extremely pure, perfectly ordered crystal of that protein, so they can fire X-rays through it and map its atomic structure. On Earth, gravity distorts the growth, producing small, flawed crystals that yield blurry data. In microgravity, crystals can grow larger and more symmetrical, revealing details that are invisible from terrestrial samples. Pharmaceutical companies have already flown experiments to the International Space Station, and the results have helped design drugs that are now in clinical trials. The market for a single crystal that unlocks a new drug target can be worth tens of millions of dollars in licensing fees or royalty streams. An orbital factory that produces a few hundred such crystals each year could generate annual revenue in the hundreds of millions. Then there are advanced alloys. Some combinations of metals like lead and aluminum simply refuse to mix evenly on Earth because one is far denser. In orbit, those alloys can be blended into a uniform material with novel properties, such as superior radiation shielding or a combination of high strength and light weight. The defense and aerospace industries would pay a premium for such materials, especially for spacecraft components that need to withstand cosmic rays without adding mass. Each of these products faces the same challenge, getting them back to Earth safely. A return capsule, like a small, reusable version of the Dragon spacecraft, can carry several hundred kilograms of finished goods from orbit to a soft landing. The capsule itself costs tens of millions to build and launch, but if it returns a cargo of protein crystals worth several hundred million, the economics are compelling. The cost of the capsule, the factory, and the launch are all fixed. The profit comes from the value of the product inside. And because the products are small in mass but huge in value, the ratio of manufacturing value to transport cost is extremely favorable. A single kilogram of Z-band fiber might sell for $50,000 while the cost to launch that kilogram and return it is less than $10,000. The difference is the profit that funds everything else. That profit, generated from Earth-facing manufacturing, becomes the seed money for space-facing infrastructure. The same revenue that pays for the Z-band furnace also pays for the propellant depot, the mining robot, and the habitat module. Earth-facing manufacturing is not a distraction from building a space economy. It is the economic engine that makes that economy possible. Every kilogram of product sent down from orbit brings back capital that can be reinvested into the next step of the journey. Every astronaut in orbit consumes roughly 1.8 kilograms of food per day. On the International Space Station, that means nearly 12 kilograms daily for a crew of 6. Over a year-long mission, that adds up to over 4,000 kilograms of packaged meals, all lifted from Earth at enormous cost. For a 3-year round trip to Mars, the numbers climb to over 15,000 kilograms just for food, plus the packaging and water needed to rehydrate it. That weight penalty becomes a crushing load on the spacecraft. The only way to break free from that dependency is to grow food in space. This is not a luxury for fresh tomatoes. It is a survival and economic imperative. Bioregenerative life support systems aim to recycle waste and produce food in a closed loop. Plants absorb carbon dioxide and release oxygen, purifying the air. They also filter water through transpiration, turning wastewater into clean vapor that can be condensed and reused. and of course, they provide calories and nutrition. The most efficient candidates are fast-growing, high-yield crops like lettuce, spinach, tomatoes, peppers, and especially leafy greens that can be harvested repeatedly. But researchers have also explored algae, which can double in mass every few hours and are packed with protein and fats. Spirulina, a type of blue-green algae, is already used as a dietary supplement on Earth. In space, a small tank of spirulina could produce a significant fraction of a crew's protein needs using minimal water and space. Insects are another option. Crickets and mealworms can be raised on inedible plant waste and provide high-quality protein. The idea may sound unappealing, but in a closed system, turning waste into food is no different from the way Earth's ecosystems have operated for billions of years. NASA's veggie experiment on the International Space Station has already shown that lettuce and peppers can grow in microgravity using LED lights and a nutrient-rich gel. The plants thrived and the crew enjoyed fresh salads. The next step is scaling up. The veggie unit is small, about the size of a suitcase. A Mars habitat will need a greenhouse dozens of square meters in area with stacked tiers to maximize growing space. MIT researchers have designed a Mars farm concept called the biosphere on Mars, which uses hydroponic towers and recycled water to produce a diet for 4 astronauts with a total growing area of about 500 square meters. That sounds large, but it would still be a fraction of the mass and volume required to store the equivalent amount of freeze-dried food for a multi-year mission. The economic trade-off is clear. A greenhouse may weigh several thousand kilograms when you include the LED panels, the water recycling system, the structural supports, and the seeds. That is a heavy upfront investment. But once it is operational, it replaces tens of thousands of kilograms of packaged food that would otherwise need to be launched over the course of the mission. And the savings compound with every month the colony exists. On the Moon or Mars, a greenhouse can operate indefinitely, producing food year after year with only maintenance and fresh seeds. The cost of shipping a single kilogram of food from Earth never goes down. The cost of growing that same kilogram locally falls over time as the greenhouse pays off its initial mass debt. There is another hidden benefit. Plants produce oxygen and recycle water, reducing the mass of life support supplies needed from Earth. A fully closed loop with plants can cut the required resupply mass by over half. That means smaller launch vehicles, lower mission costs, and the ability to stay longer without waiting for a cargo ship. Each kilogram of food grown in space is a kilogram of propellant not needed to lift supplies, and that propellant saving ripples through the entire mission design. It is a self-reinforcing cycle of sustainability. The psychological value is equally important. Fresh vegetables provide vitamins that degrade in long-term stored food, but they also provide variety, color, and a connection to something living. A crew that tends a garden is a crew with lower stress and better morale. In the monotony of a sealed habitat, the act of watering a tomato plant and watching it grow is a small but powerful reminder of home. Space agriculture is not a side project. It is the thread that weaves survival, economics, and human well-being into a single fabric. And once we master it, a colony no longer depends on the distant fields of Earth. A robot miner on the Moon cannot ask for help if its arm jams. A fuel depot in orbit cannot send a purchase order to Earth and wait 20 minutes for a reply. Every activity in the space economy depends on information moving faster than a cargo ship can fly, and that requires a nervous system woven from light. The communications spine of the entire Cis-Lunar economy will be built from large constellations of satellites, not the familiar global positioning or internet satellites we use today, but a dedicated network designed to link Earth, orbital stations, the Moon, and eventually Mars with high bandwidth, low latency connections. At the heart of this network are laser communication terminals. Instead of broadcasting radio waves in wide beams, lasers focus a narrow, intense beam of light between 2 points. That beam can carry data at rates measured in gigabits or even terabits per second, many times faster than radio, and it uses far less power and weight. 2 small laser terminals on a satellite can lock onto each other across thousands of kilometers and maintain a stable link even as both platforms move. This is not a future concept. The NASA Laser Communications Relay demonstration launched in 2021 proved that laser links from geostationary orbit to the ground can work reliably. The European Space Agency and several commercial companies are now testing laser crosslinks between satellites in low Earth orbit. The next step is to build a mesh network that does not rely on a single path. If one satellite fails or a link is blocked by Earth's shadow, the data automatically reroutes through another node. This self-healing architecture is exactly what a growing space economy requires. A lunar habitat can talk to a control center on Earth via a chain of relay satellites parked at the Lagrange points and in lunar orbit. The delay for a signal between the Moon and Earth is about 1.3 seconds each way. That is too long for real-time control of a robotic arm, but it is fast enough for voice, video, and most commands. For teleoperation, a human operator on Earth can pilot a rover on the Moon with a slight delay, using predictive software to compensate for the lag. On Mars, the delay stretches from 4 to 24 minutes, making real-time teleoperation impossible. There, the network must support high-bandwidth data dumps so that autonomous rovers can send back images, sensor readings, and video at the end of each day. That data arrives in bursts, but the network must carry it without loss. Financial transactions also run on this spine. A token representing a shipment of water must be broadcast to the network and confirmed. That confirmation travels through the same laser links, adding a few seconds of delay to an otherwise instant process. The system must be designed so that a transaction is valid as soon as it is seen by a majority of nodes, even if some nodes are hours apart. Standards become the invisible glue. Every satellite in the constellation, every habitat terminal, every rover, every depot must speak the same digital language. The international space community is already working on protocols like delay-tolerant networking, or DTN, which allows data to be stored and forwarded when a link is temporarily unavailable. The interplanetary internet, as it is sometimes called, is a reality being tested on the International Space Station and on Mars orbiters. Without these standards, a lunar miner's robot cannot talk to an orbital fuel depot's accounting system, and the whole economy stutters. A robust network does not just carry cat videos and status updates. It carries the pulse of a civilization that is no longer confined to one planet. It allows a factory in orbit to receive a design file from an engineer on Earth and start printing a part within minutes. It allows a medical officer on Mars to consult with a specialist thousands of kilometers away. It allows a stock exchange on Earth to trade futures on Asteroid platinum. The communication spine is the invisible architecture that makes all other infrastructure useful. Without it, every habitat, every mine, every factory is an island. With it, those islands form an archipelago connected by threads of light. And the next step after building that network is to decide who owns the switches, who sets the rules, and who pays for the silence when a beam fails to connect. Every ton of cargo that leaves Earth follows a long and expensive road, with each stop adding its own toll. The journey from a factory floor on Earth to a habitat on the Moon or a base on Mars is a series of distinct stages, and each one multiplies the cost. Understanding this chain is the key to seeing why local resources matter so much and why the entire space economy depends on getting the logistics right. The first stage is launch from Earth. A rocket lifts off from a pad, burns thousands of tons of propellant, and accelerates its payload to orbital velocity. That single step accounts for the majority of the total cost of any space mission, often more than half. The rocket itself is a huge piece of hardware. Even with reuse, it still requires expensive maintenance, fuel, and ground operations. Every kilogram that survives this phase has already paid a steep price in energy and engineering. Once in low Earth orbit, the payload arrives at a staging point, essentially a warehouse in space. This could be a dedicated depot or simply a parking orbit where cargo is collected and sorted. From here, the next leg of the journey begins. To reach the Moon, a spacecraft must fire its engines again to increase its speed enough to escape Earth's gravitational influence and enter what is called Cis-Lunar space. This is the region between Earth and the Moon. The delta V required for this transfer is roughly 3 kilometers per second, a significant burn that consumes a large fraction of the spacecraft's propellant. That propellant had to be lifted from Earth as well, adding to the cost. After a journey of a few days, the spacecraft arrives near the Moon. Now it must slow down to be captured by lunar gravity, a maneuver that requires another major burn. Then it descends to the surface, a final, delicate landing that uses even more propellant. Each of these maneuvers adds to the total mass of propellant that must be launched from Earth. The mathematics are brutal. The more stages you add, the more fuel you need to carry, and the more fuel you carry, the more fuel you need to lift that fuel. The rocket equation dictates that a trip to the lunar surface can require roughly 10 times the mass of propellant as the payload itself, even with efficient engines. That is why a simple delivery of 1 ton of supplies to the Moon might need a 10-ton rocket on the launch pad. Now consider the same journey, but with a propellant depot sitting in low Earth orbit. Instead of launching a fully fueled spacecraft from the ground, you launch a dry ship and a separate tank of propellant. The depot receives the propellant, stores it, and transfers it to the waiting spacecraft. That spacecraft then tops off its tanks and heads to the Moon, carrying far more payload than if it had to lift all its fuel from the ground. The depot itself is a fixed asset, a reusable gas station that can be refilled many times. Each refueling reduces the number of Earth launches needed for the next mission. With a depot, the effective cost per kilogram to the Moon can drop by a factor of 2 or 3. The next step is to build similar depots in Cis-Lunar space, for example at the Earth-Moon Lagrange points, those gravitational balance points where a spacecraft can hang almost stationary without burning fuel. A depot at the L1 or L2 point can store propellant produced on the Moon from water ice mined from the poles. That lunar propellant is far cheaper than anything launched from Earth because it was extracted using local energy. Suddenly, the economics shift dramatically. A mission to the Moon no longer requires launching all its fuel from Earth. Instead, the fuel is waiting for it in orbit, produced locally. The number of Earth launches per mission can drop by 80% or more. Now extend the same logic to Mars. The journey from Earth to Mars is far longer, about 6 to 9 months, and requires even more delta V. Without propellant depots, a human mission to Mars would need an enormous rocket, perhaps requiring dozens of launches just to assemble the spacecraft and fuel it in orbit. But with a network of depots, the situation changes. You launch a dry spacecraft to low Earth orbit, refuel it from a depot, then send it toward Mars. Upon arrival, you slow down using aerobraking in the thin Martian atmosphere, and then you land. On the surface, you produce methane and oxygen from the Martian atmosphere and water ice using the Sabatier reaction. That locally produced propellant can then be used to launch from Mars back to orbit or to refuel a return vehicle. It can even be shipped back to a depot in Cis-Lunar space, creating a two-way flow of resources. This is the logistics backbone of a multi-planetary economy. It is not a single route from Earth to one destination. It is a network of depots, tankers, landers, and tugs that move goods and fuel between Earth, the Moon, and Mars. Every local source of water or propellant reduces the number of launches from Earth, and every reduction in launches lowers the cost of everything. The backbone grows stronger as more nodes are added. A depot at Mars could supply propellant to spacecraft heading outward to the asteroid belt. A depot at the Moon could supply propellant to tugs that move cargo between Earth and Mars. The whole system becomes an interplanetary railroad, where the fuel is generated along the route rather than hauled from the starting station. And the more you invest in this backbone, the cheaper every subsequent mission becomes. That is the economic logic that will drive the expansion of our presence beyond Earth. The supply chain is not just a detail. It is the architecture of a civilization that no longer lives on a single planet. Propellant is the oil that lubricates every movement beyond Earth. Without it, no spacecraft can change orbit, no lander can descend to a surface, and no tug can push cargo between depots. The entire space economy comes to a halt if its vehicles run dry. And the most remarkable part is that the raw material for this essential fuel is the most common substance in the solar system: water. A single water molecule contains 2 atoms of hydrogen and 1 of oxygen. Run an electric current through it and the bonds break, releasing those gases. Compress and cool them, and you have liquid hydrogen and liquid oxygen, the most efficient chemical rocket propellant known. The process is simple enough to perform in a small, automated plant on the Moon or inside an asteroid mining ship. The business case for water mining is straightforward. On Earth, shipping a kilogram of water to low orbit costs thousands of dollars. That same kilogram, if mined from a shadowed lunar crater or a carbon-rich asteroid, costs only the energy to extract it and the equipment to process it. Once the mining operation is set up, the marginal cost of producing propellant in space becomes a tiny fraction of the launch price from Earth. A company that operates a water mine on the Moon could sell its output to orbital fuel depots at a price far below what customers would pay to launch propellant from Earth, yet still earn enormous margins. Those depots become the gas stations of the Cis-Lunar economy. A space tug arrives, docks with the depot, and fills its tanks with locally produced propellant. It pays for the fuel in digital tokens or through a service contract. The depot operator banks the revenue and uses it to expand operations, perhaps building a second mining site or a larger storage facility. Over time, competition emerges. A second company sets up a mine on a different asteroid and begins selling propellant at a slightly lower price. The market responds, driving costs down and improving efficiency. The price of propellant becomes a benchmark for the entire industry, just as the price of crude oil shapes economies on Earth. Storing propellant in space is a challenge of its own. Hydrogen molecules are tiny and can leak through seals and welds that hold other gases perfectly. Cryogenic temperatures are required to keep hydrogen and oxygen liquid, which demands powerful insulation and refrigeration systems. A propellant depot must maintain these conditions for months or years, slowly losing fuel to boil off. Engineers are developing technologies like passive cooling radiators, multi-layer insulation, and even zero boil-off systems that use small refrigerators to keep the tanks cold. These solutions add mass and cost, but the payoff is a storage facility that can hold a reserve of fuel for a fleet of vehicles. Without that reserve, every mission operates on short supply, vulnerable to delays. The ability to stockpile propellant changes everything. A depot with 100 tons of water in reserve can support multiple missions to the Moon or Mars without waiting for a new shipment from Earth. That buffer allows for irregular schedules, emergency returns, and expanded operations. It is the difference between a fragile outpost and a resilient economy. Cheap propellant is the single most important enabler of everything else in space. It reduces the cost of launching from Earth because vehicles can be refueled in orbit instead of carrying all their fuel from the ground. It makes asteroid mining viable because the mined metals can be shipped back using propellant produced on site. It allows human settlements to import supplies more affordably and to export finished goods. Every other industry in the space economy depends on the cost of moving mass, and that cost is dominated by propellant. Lower propellant prices ripple through every sector, lowering barriers and accelerating growth. But a system that depends on a single commodity also carries risks. A failure at a water mine could cut off the supply. A depot leak could drain months of stored fuel. Competition could collapse prices so fast that early investors lose everything. The space economy must design for resilience with multiple suppliers, redundant storage, and the ability to fall back on Earth-sourced propellant in an emergency. Managing those risks is the next step in building a system that can actually survive the harsh realities of the solar system. A single micrometeoroid the size of a sand grain can destroy a satellite worth hundreds of millions. That is the kind of risk that keeps investors awake at night. Space is not a friendly place for delicate machinery. Launch vehicles explode, solar panels degrade from radiation. Computer chips get scrambled by cosmic rays, and the vacuum itself is unforgiving. A tiny leak in a habitat wall can turn a living space into a tomb in seconds. Every one of these events is a potential financial catastrophe, and without a way to manage that exposure, the capital needed to build a space economy will never flow freely. Insurance is the bridge between risk and investment. On Earth, we buy policies for our homes, our cars, and our businesses because we know that accidents happen. The insurer collects premiums from many customers, pools that money, and pays out when a covered loss occurs. The same principle applies in space, but the stakes are higher and the data is far scarcer. Today, satellite operators purchase launch insurance to cover the period from liftoff until the satellite reaches its intended orbit. A typical policy might cost 5 to 10% of the satellite's value. If the rocket fails, the insurer reimburses the operator. That single product has enabled the entire commercial satellite industry to exist, because without it, a single launch failure could bankrupt a company. Now imagine extending that model to a lunar water mine. The mining equipment must survive a high-energy launch, a transit through radiation belts, a landing on an airless world, and then years of operation in extreme temperature swings and abrasive dust. The probability of a failure in any one component is much higher than for a satellite in a stable orbit. An insurer would need to price that risk, but without decades of historical data, the uncertainty is enormous. Actuarial tables for space habitats do not exist yet. Every new mission is essentially a unique experiment. To build those tables, the industry must start small. The first orbital factories and lunar outposts will generate a stream of operational data. Which components fail most often, how radiation affects electronics over time, and how often micrometeoroids strike. Over a decade, a body of evidence accumulates. Insurers can then calculate premiums with greater confidence. They can also require safety standards, just as home insurers require smoke detectors. A mining company that installs redundant power systems, backup computers, and extra shielding might pay a lower premium than one that skimps on safety. That creates a financial incentive for better engineering. Risk pooling becomes even more powerful when multiple operators share a common infrastructure. Instead of each lunar base buying its own expensive insurance policy, a consortium of operators could pool their premiums into a mutual fund that covers losses across the entire network. If one base suffers a catastrophic depressurization, the pool pays for repairs and evacuation. If another base loses a rover to a software glitch, the pool covers the replacement. This spreads the risk across many participants and lowers the cost for everyone. The same logic applies to cargo shipments. A container of protein crystals returning from orbit is worth millions, but it faces the risk of a failed parachute or a hard landing. A space cargo insurer would charge a premium based on the historical success rate of re-entry capsules. As the frequency of shipments increases, the premium per shipment drops because the law of large numbers brings predictability. Eventually, standard insurance products will exist for almost every activity: hull insurance for spacecraft, liability insurance for collisions, business interruption insurance for a habitat that loses power, and even life insurance for crew members. Each of these products reduces the uncertainty that investors face. With insurance, a venture capitalist can calculate the expected return on a lunar mining startup with far more confidence. Without it, every investment is a gamble on unknowns. Lower uncertainty means lower required returns, which means more projects become viable. The cost of capital falls, and the pace of expansion accelerates. An entire ecosystem of brokers, underwriters, and claims adjusters will emerge in the Cis-Lunar economy. Some will work from Earth, analyzing telemetry and satellite images. Others will be stationed at orbital depots, ready to inspect damage after a solar storm. The first insurance claim filed from another world will be a historic moment, a sign that the rules of commerce have truly expanded beyond this planet. And when that happens, the economic foundation will be strong enough to support everything else that follows. No space economy has ever been built by a single sector alone. For decades, the old model ruled. A government agency like NASA would design a spacecraft, hire a prime contractor on a cost-plus contract, and pay every dollar of development plus a guaranteed fee. The contractor had little incentive to cut costs or speed up delivery because their profit rose with the budget. That approach put humans on the moon in the 1960s, but it also produced billion-dollar overruns and schedules that stretched for years. By the early 21st century, it was clear that the traditional way could not affordably sustain a long-term presence in space. A new model emerged, one built on partnership rather than command. Governments shifted from buying hardware to buying services. Instead of NASA owning and operating a cargo ship, it would pay a private company to deliver supplies to the International Space Station. The company would design, build, and fly the vehicle, and the government would simply purchase the delivered service. This is called anchor tenancy. The government guarantees a minimum number of missions, giving the private firm a reliable customer to secure financing. The company keeps its intellectual property and can sell the same service to other customers, creating a commercial market. The results speak for themselves. The Commercial Resupply Services program let SpaceX and Orbital Sciences develop the Dragon and Cygnus spacecraft. Within a decade, they were delivering cargo at a fraction of the cost of the government-run shuttle program. The follow-on Commercial Crew program extended the same model to carrying astronauts. SpaceX's Crew Dragon now regularly ferries crews to the station, while Boeing's Starliner is still in development. The government did not disappear. It provided the initial funding, the launch pads, the deep space communication network, and the regulatory framework that made private investment possible. NASA expertise in safety standards and mission assurance remains essential. The private sector brought speed, innovation, cost discipline, and a hunger for new markets that government agencies rarely possess. Neither side can succeed alone. A purely government-led effort would be too slow and expensive to scale. A purely private effort would lack the patient capital and risk tolerance to build the foundational infrastructure that has no immediate profit. The successful model is a dance. Government builds the roads and the rules, private companies build the trucks and the factories. Together, they create an economy that neither could build by themselves. In the 1960s, we went from nothing to a moon landing in less than a decade. The timeline to a self-sustaining space economy will be longer, but the path is now visible. The next few decades divide into three distinct phases, each building on the last. The near term, roughly the 2030s, is the decade of demonstration and proof of concept. We will see the first government and private missions that extract water ice from the moon's shadowed craters and split it into propellant. A small pilot plant will prove that lunar soil can yield enough oxygen and hydrogen to refuel a lander. At the same time, the first propellant depots will appear in low Earth orbit, storing water shipped from the surface of the moon or launched from Earth at a reduced price. These depots will be the size of a small shipping container, but they will demonstrate the logistics of storing and transferring cryogenic fuel in the vacuum of space. Orbital hotels will also become a reality, not just for the ultra-wealthy, but for a growing number of researchers, journalists, and corporate clients. Companies like Axiom Space will attach their first commercial modules to the International Space Station, then detach them to form a free-flying station. The revenue from tourism and research will cover the operational costs of that infrastructure, proving that a private habitat can break even without government subsidies. By the end of the 30s, the foundational pieces will be in place. A small but reliable water mine on the moon, a handful of orbital depots, and a functioning commercial space station. The launch cost per kilogram will have fallen to under $100, thanks to fully reusable super heavy lift rockets like Starship and New Glenn. Now the midterm, the 2040s, is where the economy starts to scale. Asteroid mining will move from prospecting to actual extraction. A robotic mission will land on a near-Earth asteroid, drill into its surface, and return a few hundred kilograms of water and metals to a depot in Cis-Lunar space. That first delivery will be a historic moment, but it will also mark the beginning of a new commodity market. The cost of propellant in orbit will drop sharply because the asteroid water costs only the energy to extract it. Manufacturing exports will also begin in earnest. Small orbital factories will produce ultra-pure optical fibers and protein crystals for pharmaceutical companies on Earth. The revenue from those products will fund the expansion of the factory fleet, creating a positive feedback loop. A pilot space-based solar power satellite will be tested in geostationary orbit. It will be small, generating perhaps 10 megawatts of power, but it will prove that beamed energy can reach the ground with acceptable efficiency. Governments and utilities will watch closely because the promise of clean, continuous power from space is exactly what a warming planet needs. The 2040s will also see the first permanent habitats on the moon that are not just science outposts but real settlements. A small village of pressurized modules, buried under regolith for radiation shielding, will house a rotating crew of researchers and miners. They will produce their own water, grow some of their own food, and manufacture basic spare parts using 3D printers supplied with local regolith. The moon will no longer be a place we visit, it will be a place we live. By the late 40s, launch costs may fall to around $50 per kilogram, and the ISRU industry will be mature enough to support a robust Cis-Lunar transportation network. The long term, the 2050s and beyond, is when the economy becomes truly self-sustaining. A permanent colony on Mars will establish its own industrial base, mining water from the subsurface and producing methane and oxygen using the Martian atmosphere. That colony will trade with Earth and the Moon, exchanging Martian resources for high-tech goods that cannot yet be made on the Red Planet. A full-size space-based solar power station will begin sending a gigawatt of clean energy to Earth, generating billions in revenue each year. Asteroid mining will expand from near-Earth objects to the main belt, opening up a vast new supply of platinum group metals and rare earth elements. The economic activity in space will generate its own demand for services: banking, insurance, construction, repair, waste management. A truly independent economy will have emerged, one that no longer relies on Earth for its survival. But all of this rests on a single fragile assumption: that launch costs continue to fall and that ISRU technology works at scale. If those two pillars hold, the timeline is aggressive but plausible. If they stall, the whole schedule slides. The next 2 decades are what historians might call the starving time. Revenues from tourism and satellite services are real, but they are small compared to the investment needed to build the infrastructure for mining and manufacturing. The early players will burn through billions of dollars before they see a positive return. Some will fail. A few will survive and become the anchor companies of the new economy. The window of risk is narrow. If we can push through that starving period, if we can keep funding the depots, the mines, and the factories long enough for them to reach profitability, then the space economy will reach a tipping point after which growth becomes exponential. The cost of propellant drops, the cost of manufacturing drops, and every new project becomes cheaper than the last. The first generation of space settlers will not get rich quickly, but they will lay the foundations for a civilization that will. Those foundations rest on 7 pillars, each essential and none sufficient alone. The first is cheap launch, the ability to move mass from Earth to orbit for tens of dollars per kilogram instead of thousands. Without that, every other activity is strangled by the gravity well. The second is in-situ resource utilization, learning to extract water, metals, and building materials from the Moon, Mars, and asteroids. That breaks the umbilical cord to Earth and allows growth on local resources. The third is abundant energy, whether from the Sun in orbit or from fission reactors on the surface, because without power, no factory runs, no habitat breathes, no fuel is produced. The fourth is legal clarity, a framework of property rights, contracts, and dispute resolution that gives investors the confidence to commit billions. The fifth is logistics, a network of depots, tugs, and standardized containers that move propellant, goods, and people between destinations. The sixth is human infrastructure, habitats that protect against radiation, provide closed-loop life support, and offer a quality of life that makes long-term settlement possible. And the seventh is risk management, insurance and safety standards that spread the inevitable failures and prevent them from derailing the entire enterprise. These 7 pillars do not stand in isolation. They are woven together, each one reinforcing the others. Cheap launch makes ISRU more affordable. ISRU produces propellant that lowers the cost of logistics. Abundant energy powers the factories that manufacture the components for habitats, and legal clarity unlocks the capital that builds the whole system. A breakthrough in any single area reduces the burden on the others, and a failure in one can stall them all. This is why the space economy is not a single invention or a single discovery. It is a system of interconnected breakthroughs, each one made possible by the progress of its neighbors. Building that system will take decades, billions of dollars, and the combined effort of governments, private companies, and individuals who are willing to bet on a future that does not yet exist. It will require patience because the early returns will be small, and many ventures will fail before the rest succeed. But the alternative is to remain permanently bound to a single planet, with all of our eggs in one fragile basket. Earth has given us a beautiful home, but it also has limits. Resources grow scarce, the climate changes, and the population continues to grow. Expanding into space does not mean abandoning Earth. It means creating a safety net, a source of clean energy, new materials, and new opportunities that can help solve the problems we face here. The first steps are already being taken. Reusable rockets are flying. Water ice has been confirmed on the Moon and Mars. Private companies are building orbital habitats, and the first asteroid prospecting missions are in development. The path is visible, even if the distant end remains hazy. Every person who watches this video and shares the idea, every student who studies engineering or law with space in mind, every investor who supports a space startup, Every voter who encourages their government to fund exploration becomes part of that journey. The space economy will not be built by a handful of heroes in silver suits. It will be built by thousands of people working across disciplines and across nations, slowly assembling the pieces until one day we look up and realize that humanity has become a multiplanetary civilization. And when that day arrives, the economy that makes it possible will not just be a collection of rockets and mines. It will be the most ambitious system of cooperation and exchange our species has ever created, a testament to the idea that the future belongs to those who dare to build it.